பொறியாளர்களே நாட்டை கட்டி எழுப்புகிறார்கள். தரமான பொறியியல் கல்லூரியே திறமைகளை வெளிக்கொண்டு வரும். புது உலகை படைக்கும் பொறியாளர்களை உருவாக்கித் தரும். Sri Balaji Chokalingam College of Engineering. ACS Group of Educational Institutions, Arni. திறமையான பொறியாளர்களே நாட்டை கட்டி எழுப்புகிறார்கள். தரமான பொறியியல் கல்லூரியே திறமைகளை வெளிக்கொண்டு வரும். புது உலகை படைக்கும் பொறியாளர்களை உருவாக்கித் தரும். Sri Balaji Chokalingam College of Engineering. ACS Group of Educational Institutions, Arni. திறமையான பொறியாளர்களே நாட்டை கட்டி எழுப்புகிறார்கள். தரமான பொறியியல் கல்லூரியே திறமைகளை வெளிக்கொண்டு வரும். புது உலகை படைக்கும் பொறியாளர்களை உருவாக்கித் தரும். Sri Balaji Chockalingam College of Engineering. ACS Group of Educational Institutions, Arni.
A very good morning to one and all present here. Hope everyone is safe and healthy. First, I would like to start with a quote. Invest your energy into something that is going to contribute to your growth. With this, I am Radha Chailakshmi, shall be your host for the day. Welcomes you all for the webinar on the topic Artificial Intelligence and IoT in Manufacturing. Organized by Department of Mechanical Engineering, Sri Balaji Chockalingam Engineering College, Arni. It gives me immense pleasure to extend a warm welcome to our chief guest and speaker of the day, Dr.Ramesh Sengottuvelu, Professor, Presidency University, Bangalore. I would also like to give my heartiest welcome to our eminent organizer of this webinar, Dr. TamilNadu, Principal, Sri Balaji Chockalingam Engineering College, and Dr. Ismail Khalilullah, Technical In Charge of our research studio. AI, that is artificial intelligence, which is not a new subject to us. In fact, we are already using in our day-to-day life. AI is an interdisciplinary science which is based on the principle of human intelligence in machines. As AI is being used across different industries, including finance and healthcare, which is also plays a major role in autonomous vehicles. Understanding this concept, our institute is organizing this webinar on the topic Artificial Intelligence and IoT in Manufacturing. I now request Mr. Gnanasegaran, Head Department of Mechanical Engineering, to deliver the welcome address.
Very good morning to one and all. In our department is organizing the webinar in the topic of artificial intelligence and Internet of Things in manufacturing. It gives me an immense pleasure to deliver a welcome address on this special occasion. I am very much happy, privileged to gratitude to welcome our benevolence founder chairman, Thiru A.C. Shanmugam sir, and my hearty welcome to our president, ACS Arun Kumar sir, and Thiru Vice Principal sir for giving this opportunity to conduct this webinar to enhance our knowledge. And I would like to welcome our respected resource person and eminent personality of the day, Dr. S. Ramesh sir, Professor in Department of Mechanical Engineering at Presidency University, Bangalore, who has agreed our concern with this busy schedule to share his knowledge to faculty and students community. Welcome you, sir. Next, I would like to welcome Dr. Manivannan sir, Dean Phase 2 Campus, Dr. MGR Educational and I like to welcome our technical team, Dr. Sir, Vijayalakshmi ma'am, and our host, Miss. I welcome the various department HODs and faculty of our college and various college participants. Last but not least, finally, I welcoming our young budding engineers from our college and other college. In this situation, definitely this webinar will enhancing the skill test of our teaching community. I hope you all having a great exposure in this session. Once again, I welcome you all gathering. Thank you.
Thank you, sir. Now I call upon Mrs. Vijay Lakshmi to introduce our today's chief guest.
A very good morning to one and all present here. I'm really honored to introduce our beloved chief guest, Dr. S. Ramesh uh, Sengottuvelu, Professor, School of Engineering, Presidency University, Bangalore. Dr. Ramesh graduated with bachelor's degree in Mechanical and Production Engineering from Annamalai University, Chidambaram, and his master's in Mechanical Engineering with a specialization of manufacturing from IIT Madras, Chennai. He received his doctorate degree in Mechanical Engineering at Anna University, Chennai. He has over 25 years of teaching experience, 2 years of industrial experience. He served in Ethiopia at Mekelle University under the Ministry of Higher Education sponsored by UNDP. He also worked in Oman for 2 years. He has various administrative positions in premier institutions. He has contributed 9 research scholars till date, and currently he is guiding 9 research scholars. He has contributed more than 82 publications in international journals. His sustained contribution to teaching helps in fulfilling the nation's aspiration regarding the higher education. His commitment, hard work, and education have made him an inspiration among the workers and students. We really thank him for accepting our invitation such a short notice and deciding to help us during this lockdown situation. Now, I would request Dr. S. Ismail Khalilullah, our technical in charge, to play a small introductory video to know more about your chief guest.
All present here. It gives me great pleasure in introducing our chief guest, Dr. Ramesh Sengottuvelu, Professor, School of Engineering, Presidency University, Bangalore. Dr. Ramesh did his BE in Mechanical and Production Engineering at Annamalai University, Chidambaram in 1989. He did his M.Tech Mechanical Manufacturing Mechanical Engineering from College of Engineering, Anna University, Chennai in 2008. His professional experience, he has over 30 years of teaching and industry experience. He started his career as a lecturer in Shankara Institute of Technology, Coimbatore. He worked as a QC engineer in Coimbatore Pistons Private Limited in Coimbatore, maintenance engineer in Kandasamy Textiles, Bhavani, lecturer in Bharat Institute of Engineering and Technology, Chennai, lecturer in Hindustan College of Engineering, Chennai, assistant professor, Satyabama University, Chennai, assistant professor, Mech University, Ethiopia, Professor, Satyabama University, Chennai, lecturer in Salala College of Technology, Oman, Professor and Director, Excel Engineering College, Komarapalayam, Professor, Sona College of Technology, Salem, Principal, Annai Madammal Sheila Engineering College, Namakkal, Principal in Beltech High Tech, Dr. Ara, Dr. SR Engineering College, Professor and Head, KCG College of Technology, Chennai, Professor, KCG College of Technology, Chennai, and Professor, Presidency University, Bangalore, currently. His guideship details. He has guided 9 research scholars and he is currently guiding 9 research scholars. His other academic and research experience, he is a managing editor in MMSE Journal Editorial Board. He is a PhD thesis examiner in Anna University, Satyabama University, and Gujarat Technological University. He is a reviewer in International Journal of Manufacturing Engineers, International Journal of Composite Materials, International Journal of Measurement, International Journal of Intelligent Manufacturing, International Journal of Vibration and Control, and International Journal of Experimental Techniques. He's attended over 30 international conferences and 10 national conferences, and he has been invited more than 10 conferences and lectures as a resource person. His publications and projects. He's published over 63 research papers in international journals and 7 in national journals, 33 papers in international conferences and 10 in national conferences. He has 3 book publications and 1 patent. Some of his awards and achievements: he received the Dr. APJ Abdul Kalam Award for Innovative Research from Society of Engineering Education Enrichment, Best Administrator Award from Dr. Kalam Educational Trust, Certificate of Reviewer Contribution Award twice from the International Journal of Precision Engineering and Manufacturing Springer Publications, Best Paper Presenter Award in International Conference in Computational Methods, Engineering and Health Sciences, Malaysia, Who is Who in the World from Marquee Biography Pearl Anniversary, Appreciation Award for 100% Result PG 6 times from Sona College of Technology and KCG College of Technology, and Best Teacher Award from Satyabama University. His areas of expertise and research interests: machining of aerospace alloys, titanium alloys, and other difficult materials to cut, composite materials, nano-composite materials, characterization, performance study of advanced cutting tools, modeling of machining processes using artificial intelligence tools, performance study of advanced machining, micromachining processes. Some of his academic and professional membership: he is a member in Institution of Engineers, Indian Society of Technical Education, American Society for Mechanical Engineers USA, Powder Metallurgy Association of India, Aeronautical Society of India, Society of Automotive Engineers India, and Tribology Society of India. He has visited Ethiopia, Sultanate of Oman, Malaysia, and United Arab Emirates. He has a citation of 807 and a H index of 12, ITIL index of 14 in Google Scholar, and a H index of 12 in ResearchGate. On behalf of Sri Balaji Chockalingam Engineering College, we really thank him for gracing us with his presence and wish him good luck for his future endeavors. Thank you.
Thank you, ma'am. Now the most awaited time has arrived. Without any further delay, I invite our eminent speaker, Dr. Ramesh Sengottuvelu, to proceed with his presentation. So we request you to take over the session, sir, and enrich us with your knowledge.
So, at the outset, I would like to say thanks to the management of MGR Group of Institution, and especially Sri Balaji Chockalingam Engineering College Principal Professor Tirunavukarasu and HOD Professor Gnanasegaran, and my special person Dr. Manivannan, Dean Phase 2. So I'd like to say thanks to everyone, and finally I'd like to say thanks for the audience, those who are all going to listen my session today's way. And the topic which I am going to handle today is actually IoT and artificial intelligence in manufacturing. In fact, I thought of handling these two entity of the current technology. That's what I felt actually. Then with this IoT and AI alone cannot do the manufacturing upgradation. So I felt industry 4.0 will give you the exact outcome of the presentation. So let me start this presentation with a video, then I will continue the whole presentation. So for the glimpse of what is industry 4.0, all those things we can understand from the first video, then we can proceed the full presentation. I will share the screen. So the title is IoT, Artificial Intelligence in Manufacturing. So I'm going to focus industry 4.0. The first video I would like to play before starting my presentation to have some knowledge about this IoT. Okay. So now I would like to start my session. So this whole session, I'm going to cover the introduction of Industry 4.0 and the elements of Industry 4.0 and some examples of 4.0, how effectively the industries they are utilizing it in their day-to-day activities, and requirements for any engineers if they want to introduce Industry 4.0 means what they have to do. These are the things are inside. Let us move inside. So this is a simple example what we used to see day to day activity. That means to make a floor, our olden days, our grandparents, they used some grinder in their home to grind the floor by manually. So then after some evolution happens, that means the steam engines, it is started coming into that exposure. Then they started using that steam engine. From that they grind the floor. Then the evolution, next evolution, that the steel it is coming into that practice. Then they prepared the grinder machine. And now nowadays it is the floor which is made a continuous process monitoring devices, and automatically it is packed and is coming out to the market. So this is how the floor itself, the making floor itself, it has some evolution, right? So from olden days to the present day. So the same way that industry revolutions, it has there are stages. The level of complexity is the matter in this industrial evolution. Okay, so the industrial evolution, the first level, it is introducing the mechanical production machines powered by water and steam. It is evolved in the period of around the end of 18th century. Okay, that is the more complicated one, but that time it was not like that. Then some technology development, the second industrial evolution, it came during that time. The introducing invention of steel, it is started, and mass production lines, it was there. And this all powered by electric drives. This is the second industrial revolution, and it is happened the beginning of 20th century. Okay, and the third industrial evolution. Okay, so in that through the use of electronics and information technology, further progression in autonomous production, it takes place in this case. So in fact that industrial evolution, third industrial evolution, we found all computer came or CNC machines came, everything came, but it is an indigenous machine. It does its work. Whatever the instruction we are giving, it does. Okay, so it does not go beyond that level of instruction. Whatever the human, it is they are giving, it does not gone more than that. So this evolution, it came around the beginning of the 1970s. So now the present day, what we are in the world, it is actually industrial evolution. In fact, the computer science is booming, information technology is booming. So everything is booming nowadays, and along with that interrelated departmental things, now mechanical supposed to join with that hands with information technology, and sort of utilizing that internet of things scenario. Everything is there in the field. Okay, so this industrial evolution, the fourth industry 4.0, it is a industrial evolution based on the cyber-physical systems. That means the difference between the industry 3.0 and 4.0, it is nothing but here it is done all by electronics and IT components, but the data are recovered in the means of cloud computing. There, that all the data which is taken care, and by using the data, the production levels are upgraded, and it gets some advancement. That is the today's technology. So that's what here I mentioned actually the level 1, level 2, level 3, level 4. So the level of complexity is getting increasing, in fact. Okay, so because of the technology only, it is in the today's position. So now let's see the next thing. Clearly I want to discuss that from which year to which year that industry 1.0, industry 2.0, industry 3.0, it was there. That industrial evolution, first industrial evolution, it is in between 1760 to 1830, and industrial evolution between 1870 to 1914. And industrial that means the period between this period there is no progress in the developments. Okay, so whatever it is evaluated, that people they utilized during this break period actually. In fact, the third industrial evolution, it is 1970 to 2000, and the fourth industrial evolution, we guess that it goes up to 2050. Even it may end up with earlier date also, maybe 2025 or 30, it may be over. Then remaining periods, we are going to use this technology only for the next phase of evolution. That's what is going to happen. So this is the industrial evolutions, what the period wise. Here, the industrial evolution in 1760, the energy what we used actually, the steam power and the mechanization of processor or development of mechanical machines. So by using the development of mechanical machines, some factories are established, like textile, iron, chemical industries, which is developed during that period, the first industrial evolution period only. So whatever the products which is developed during that period, which is moved by using locomotives, by logistics purpose and all. Okay, so the locomotives also developed, and by using that, the logistics is taken care. That's what. And here are some typical examples of that industrial evolution. This is the Watt steam engine, which is developed in 1770. And for this, whatever the machine it is there, it's supposed to have some feedback system. Okay, here it is feedback is also a mechanical device, that is Watt's governor. That's what that is developed during that period. So we should take care the feedback for every stage. It's supposed to be there. So in this stage, the feedback thing is actually the Watt's governor. It is, I think, mechanical students, you might have studied this kind of how the Watt's governor it is working, etc., etc. And the next example, it is a weaving factory powered by central steam machine, which is shown here. You can see that all weaving factories, all machines, different machines, weaving machines, which is continuously connected by means of pulley and belt arrangements. So these pulleys are operated by means of steam machines, steam engines. Okay. Then next one is the second industrial evolution. It is in 1870, which is evaluated. So the energy which is used in this is actually electric power in factories, all the factories. And during that period, telecommunication has been developed through telegraph and telephone aspect, and the machining also, which is developed in the Subfloor conventional machining, like turning, drilling, and milling, like kind of operations. And the automotive industries gets boomed up. Okay, the series of large production is taken place there. The people, they started analyzing their process by manufacturing methodologies. They created the methodology, as well as the study of time and moves within the operations. The operation times they studied, and they tried to improve the machining sequences. This was happened in the second industrial revolution itself, and the better management perspective is initiated. And in fact, the electromechanical controls also developed during that period by using the relays concept, and petroleum industries also developed during that period. And here the feedback control, which is used actually open loop control or closed loop control through the operator. Operator has to monitor this open loop and closed loop conditions. And these are some examples. Automotive assembly line of Ford Motor Company, which is developed. And this is the electromechanical controls in a factory by using the relays concept. And in the third industrial revolution, 1970, here actually the process automation, which is developed by using feedback loop control and sensors and actuators. And during that time only the CNC machines has arrived and replaced that conventional machines. And the communications which is developed through program logic control and robotics protocols. Okay, and the data which is recovered like synoptic and production history from there. And because of this all the efficiency and quality assurance which is created during this period only, the efficiency of the product and quality of the product, everything is monitored through the efficiency and quality assurance category only. And this is the examples of some products which is industrial automation by program logic controller, and the industrial automation by modern PLC cabinets. And this is the industrial application automation by SCADA and manufacturing evolution systems and ERP and synaptic and data log for Subfloor. This is the whole Subfloor which is monitored by SCADA, MES and ERP, all those things. It's a computerized control only. And the third industrial evolution, some shortfalls we found. So what are the shortfalls in the sense? Actually, it is actually improved the productivity and the product quality and cost reduction through automation. That is fine, fantastic. And the high level of discipline and management methodologies also, which is improved way. And like sensors, actuators, data acquisition we used, but still no machining reasoning is developed. So that means the machine is not started thinking their own style. Okay, so the machine language, that means the machine and another machine, it is not able to talk each other. That thing is not happening. So that's what the no machining reasoning. What is the best decision when some expected event happens? So that means why it is started, actually the shortage of raw material when the production is going on. And when the human, when he is saying that there is no raw material, then only we understood that there is no raw material. Okay, and the demand of changing, that means the customer end, there is some demand. If I need this kind of product instead of this configuration, like that some demand is coming, means the demand is not intimated to the machine, etc. The machines only following orders. That means the machine, it takes the order from the human and it does that work. Okay, so that means now we are thinking that why don't we give directly the instruction to the machine like some channel. That's what the evolution of fourth industry evolution. So now the still highly dependable on human, like data analysis. That means whatever the production it is going on. Okay, today this 8-hour runs the machine, and these many components which is manufactured, and where is the problem? It's like some analysis it takes place, that data analysis. Okay, and production control and planning, forecast analysis, production ordering, defining manufacturing sequencing, grouping of operations, setup for production. These are all, everything is done by the human only, dependable only the human. But now the fourth industrial evolution, it's comments in the 2015 onwards. The new scenario which is started, like the scenario that says the demand for highly customized products and short product life cycle. That means the product which is in the usage, it goes off very fast. So we need to meet out that next level of products. Okay, then highly competitive markets. So there are a lot of competitors that are coming. So you need to match their customers expectations. And environmental restrictions, these are all the day-to-day scenario. It happens in the industries, they are not able to face these demands from the outside. And customization, so highly flexible production lines are required to meet this demand. And productive and cost effective also is required. When you are spending more amount, you need to take it back very fast. Okay, that's the productive and cost effectiveness should be there. And make to order. Okay, so these are the customization they started thinking about. So the technologies we implemented in the fourth industrial evolution is actually automation, robotics, we brought it into that, and artificial intelligence, big data, cloud computing, simulation, and internet of things, cyber security. These all the technologies which is brought into that fourth industrial evolution. Now, this is the some scenario which is available in the present day industrial fourth industrial evolution, that is industry 4.0. So let me give you a video to explain this industry 4.0. Then I will proceed further.
The Internet of Things has the potential to increase global productivity up to 25% by 2025, which could translate to an economic value of $11 trillion. Industries like manufacturing are embracing the potential of the Internet of Things. Many production facilities are already using processes and supervisory control systems with connectivity. The Internet of Things for manufacturing is a family of solutions that combines the capabilities of analytics, cognitive computing, and the Watson Internet of Things platform to drive operational efficiency across the factory value chain. This solution benefits the manufacturing industry in three main ways. First, it helps plants get 100% efficiency out of their equipment by identifying and solving issues before they cause delays. Second, it makes processes and operations cognitive, so plants can produce maximum quality and yield from raw materials and manufactured components. Lastly, it helps plant managers better manage resources, improve worker expertise, and provide a safe working environment. Advances in these three areas define a new wave of connected manufacturing, one that revolves around things, process, and people. Let's take a look at how this works for Simon, the plant manager for an aircraft manufacturer. Simon oversees the production of key components for large commercial aircraft, and his top priorities are meeting production deadlines and producing airplane parts safely and efficiently. One of his biggest clients needs to move up their delivery date by 3 months. Simon and his team use the Internet of Things for manufacturing, which will help them deliver earlier than originally planned. An equipment analytics solution identifies problems with equipment health and performance before they happen and prescribes maintenance procedures so Simon's team can avoid equipment failure and downtime, getting maximum effectiveness out of their equipment. To ensure the components are meeting quality standards in normal production, Simon uses a quality analytics tool to identify variability in the manufacturing process in real time. This allows equipment operators to make adjustments to process parameters based on plant conditions that could affect the quality of production. By monitoring quality in real time, Simon's team can avoid producing faulty components, ultimately saving time and money. Another priority Simon has to account for under a rush schedule is the safety of his plant workers. The cognitive IoT platform includes worker safety technology that monitors things like exposure to extreme heat or toxic gas, open flames, and operating dangerous machinery. The plant workers wear sensors in their helmets and wristbands that provide real-time alerts on working conditions, activating preventative measures if physical well-being is compromised or safety procedures have not been applied. Because the platform allows Simon to track all of this Internet of Things data in real time, he can be confident that the production equipment, tools, and employees will be able to safely take on an accelerated schedule and make plans to move forward. Once the completed aircraft from Simon's plant is put to use, those manufactured parts continue to generate data over time, data that designers and engineers can use to make improvements and updates to each part in the future. Additional sensors also make it possible for Simon's plant to offer cognitive solutions to the airline to help with ongoing predictive maintenance of each manufactured part. Using the power of the Internet of Things paired with cognitive computing and analytics, companies across all industries will improve the way they design and manufacture connected products, products that will change the way we work and live.
Okay, with this introduction of the Internet of Things in manufacturing, we'll proceed to the Industry 4.0 as a smart factory that I want to introduce. That smart factory, what is the smart factory actually? It is a collective term for technologies and concepts of value chain organization. Actually, that value chain organization in the sense actually the horizontal and vertical value chains are there. The vertical in the sense actually we can talk about the starting from the design to till the service. It is the vertical value chains, we can term it. And then horizontal value chains, it is actually the customers and suppliers, and then the key partners. They are all considered as the horizontal value chain components. Actually, it is based on the technological concepts of cyber-physical systems, the Internet of Things, and Internet of Services. Now you see these value chains and digitization of value chains through Industry 4.0. Here you see the bottom, actually, the digital world to real world. It should happen based on these 5 stages. Okay, the stages are the product design, which is in the design stage. Actually, the second stage, actually, the production planning, how the product need to be launched outside, that need to be planned properly, production planning. And the production engineering, that means we need to choose that which machine is better for completing this particular operations. Like that, the production engineering department will work on about choosing machine and sequence and everything. And the real production takes place in the fourth stage. And services, it is after the product is over, it goes into the user area, that means the customer end, that is the services. If they find any difficulties, that can be sought out by the services areas. Okay, so these are the digital world to real world. There are different sequences. These sequences are called the value chains. In this, each and every link, it has a value. Okay, so now if I want here some elements are there here. The simulation means, actually, the before thinking about the product, you need to plan in computer itself simulation. Okay, that is that will go till the production engineering. Okay, so there is no raw materials required or machines required for this stage, actually. So you can simulate and see the product, how it will looks, that we can do it in the period. And the product life cycle management means it is from the stage 1 to and up to the services, the whole life of the product management, that need to be think. And the manufacturing execution systems, it is in between that the production planning to and production level. Okay, and totally integrated automation means once the real production starts, then only that automation is a matter. So the totally integrated automation, it comes into the production engineering and production area only. Okay, so this is the value chains of any product and any components. And here the digitization of the value chains, here that these are the entities need to be considered in each and every stages. Okay, so here engineering, design tools and simulations, and life cycle data management, and digital manufacturing, these are all the different entities need to be taken care. And each and every data which is obtained in this entity, this is transferred into the cloud computing. Okay, so there we can pick the required data and do the analysis, and we can modify that requirements and go for the next level of product development. Okay, this is what that value chain and digitization of the value chains through Industry 4.0. And here, actually, for any Industry 4.0 need to be constructed by means of some supporting elements. Here there are 9 supporting elements are there. So these 9 supporting elements is defined as pillars of Industry 4.0. Okay, so the autonomous robots, starting with the autonomous robots, that is actually a robo which can operate on its own. Okay, that means it knows what is the final achievable thing, and what is that like that human, he can give the instruction to the machine, no, that is nullified, and the autonomous robots is taken care of that job. And the simulation part, and software integration, and industrial internet, cyber security, cloud, and additive manufacturing. Okay, so that means the cloud computing, I want to tell something. In that olden stage, we used actually the file transfer protocols. That means whatever the about a product means, there are some valuable data which is stored in that file. Okay, so we can take that values, and we can do that modifications in that next level of product. But in this case, the cloud computing, it is able to give you the data sharing, all those things for the further products. That's what that like it is actually FTP, file transfer protocols, like that. And additive manufacturing, actually this additive manufacturing is the major wonderful technique which is implemented in the IoT concept itself. That means now by using this additive manufacturing, there are a lot of products which is developed and utilized in the modern day industries. Like a simple thing, that biomedical components, and then developing biomaterials, which is the hot topic in this additive manufacturing areas. Okay, then this augmented reality, AR, like that something it is there. Actually, virtual reality is there, and augmented reality is there. Actually, virtual reality means you can see how the things are happening, and you can realize how things are working, and you can feel that you are working in that place itself. But augmented reality, it is actually to make some additional realization. Okay, that means which is not exactly not required, but if you provide that means it will be additional value, like that. That is the augmented reality concept. And the big data and the analytics, that is the whatever the data which is stored in the cloud, that can be analyzed by 3 V's, like the variety and variable and volume, all those things which is available in the big data. In that you can analyze whatever the data required, and how to improve the production flow. Everything can be done in that big data and analytics. This is the 9 elements which is more useful in the industry 4.0. And here I would like to show one more video. That is a final video of our presentation.
A vision of tomorrow's manufacturing. Products finding their way independently through the production process. In intelligent factories, machines and products communicate with each other, cooperatively driving production. Raw materials and machines are interconnected within an Internet of Things. The objective, highly flexible, individualized, and resource-friendly mass production. That is the vision for the fourth industrial revolution. A bottling plant for liquids, set up together with Siemens, is used to demonstrate the most important components of the intelligent factory of the future. Each bottle contains an RFID chip storing a precise description of how it has to be processed. Which liquid, which lid, and which label. At each station, the bottle communicates directly with the machine, telling it how it has to be processed. At the end, the computer checks whether the bottle has actually been produced as desired. Factories with networked machines and products are already in existence today. In the future, however, these hitherto self-contained systems will be connected together in a comprehensive network. All devices, machines, and materials will be duly equipped with sensors and communications technology and connect to each other. These systems are known as CyberPhysical Systems. The highlight is that they communicate with each other and also control each other cooperatively.
Wenn Sie sich das Thema Industrie 4.0 angucken, dann basiert sie ja auf der Logik dieser Cyber-Physical Systems. Das heißt, Sie haben autokrate selbst arbeitende Systeme, die sich optimieren und sich gegenseitig austauschen. Und dadurch letzten Endes Produktion optimieren.
Ja, die Vision sieht so aus, dass wir ein Internet quasi hinunterziehen bis auf die unterste Ebene. Das heißt, jeder Sensor, jeder Aktor wäre damit quasi ein Teilnehmer eines Internet der Dinge. Jedes Gerät hat damit eine eigene IP-Adresse, ist damit adressierbar in diesem Netzwerk.
For the customers, this means tailor-made products at relatively affordable prices. For industry, it means highly flexible mass production that can be rapidly adapted to market changes, because in the future, product life cycles will be even shorter. Another reason why it's increasingly important to depict engineering across the entire life cycle. Maintenance, for instance, is planned in from the very start.
Wir haben ja bereits in den 90er Jahren mit Totally Integrated Automation ein Setup gewählt, wo unsere Produkte und Systeme sehr gut miteinander kommunizieren können.
At Corporate Technology in Princeton, a cyber-physical control is being researched even today. The vision, the control, and all linked sensors are connected to the internet.
One potential scenario is enabling the PLC to react to utility pricing information in building automation. We can enhance PLCs to use simulation to calculate how much to pre-cool a building, with the ultimate goal of turning off the cooling system during peak times.
But that's just the beginning.
We prototype capabilities in the PLC to access big data in cyberspace in real time. And we have also enabled a network of PLCs to connect to a dynamic simulation of the entire physical process.
Siemens is shaping the future of industry. Connecting the real with the virtual world of production is making it possible to enter entirely new dimensions in quality, efficiency, and flexibility. The company is well prepared for Industry 4.0.
Okay, fine. So with this background, that Industry 4.0 and how the machines are connecting with each and every machines. That means the machine to machine, how it is communicating their language in the sense of sensors that we have seen in this slide. And now you see this is the digital twin shop floor. This is the important thing in any modern manufacturing industries actually. So here actually I want to emphasize this how it is operating. Okay, so the digital twin shop floor actually the how to optimize the production and decisions in unexpected situations through intelligent computations. Okay, so that means it is creating virtual environment integrated to physical production and management systems. Okay, now here I want to tell you that this is the physical shop floor, this portion. Okay, and this is the virtual shop floor. Okay, so now these floors are operated by centrally the shop floor digital twin data which is available in this central part. Okay, so now here from this virtual shop floor the data are transferred to this shop floor digital twin data, and from this physical shop floor also the data is transferred to this shop floor data. Okay, and then here before producing any production, that means here the actual production need to be happen in this point, but the virtually before starting the actual virtually the same product which is taken over in this virtual shop floor, and the quality and size and the requirement of the parameters which is verified in this virtual shop floor itself, and then that required data which is passed to the shop floor digital twin data, and then from there which is the data are driving this physical shop floor actually. So that's what here you can see the iterative optimization it will take place in this point. So that means it will compare this physical shop floor and virtual shop floor, and it gives the exact required data to the shop floor digital twin data. Okay, that is what here takes place, the interaction and mapping. That means mapping towards the right dimension and right size and right quality. Okay, so that takes place between these two elements. And the same way here this shop floor service system also it will give some data to the shop floor digital twin data. Okay, that means the customer end and the management end, there are a lot of data it will flow to the shop floor digital things. That means supply chain management, product life cycle management, and ERP, MES, PDM. These are all in experience they generate some data and it will proceed to the shop floor digital twin data. Okay, so this also it will compare with this shop floor service system and physical shop floor, and here also it will compare the virtual shop floor and shop floor service system, and it creates the interaction and gives the exact required data. So these three things will operate balanced way, and it gives exact dimensions. That's what it is optimizing the production and decision in unexpected situation through the intelligent computations that takes place inside these arrangements. Okay, and the implementation for how the physical shop floor which is implemented by means of sensors and automation embedded modules and generate and integrate data. And the main challenge it is different protocols available. It's a Modbus and Profibus and industrial Ethernet are there, and virtual shop floor it is gathering the information from CAD CAM systems and simulation systems and the management systems. Example, able to translate 3D drawings into CNC code, and then it is simulating the production sequencing. They are writing the production sequences, sequencing it through virtual copies of actual operational stations, and constantly updated by information received from the physical shop floor PS. And how the service system and digital twin data, here it provides the data from PS physical shop floor and virtual shop floor, as well as receive data from both, generating fused data that converges all data received from real production and simulation. So that's what is happening here. It is converging between virtual and physical systems. It takes place Internet of Things collecting and providing data, powerful cloud computing enabling big data and artificial intelligence, and quick reactions regarding planned and actual production, and real-time decision making through data analysis, and modern industry-based high connectivity, that is a cyber physical systems. We will be the major player in this highly connectivity in this case. Now you can see this, what is cyber physical systems. Cyber physical system is a smart system that communicates, controls the physical components and computational components through digital networks. Here you see this diagram. Here, this is the embedded system. This is the ones maybe a few years back. The embedded system is the hot topic in the electronics field. Then it is you can see that smart sensors is available now. By connecting this embedded system and smart sensors, we can create the smart systems, smart sensors and actuators, which is created. And this is the, by connecting this sensor and the actuators and the embedded system all together, here it is named as cyber physical systems. Okay, so this thing can monitor any kind of data, cloud data and the physical system that can be taken care by this cyber physical production system, CPPS. Okay, so this is the simple illustration for connecting this cyber physical systems informations, which is connecting this communication control, which is taking care this communication control, and it is computing the digital networks also. Okay, that's what the cyber physical systems will do. And here how it is in the working system. Here is the functional integration. That means that it is in the working spot, different machines which is working together, and the data are available in that cloud data, that integrated cyber physical system which receives that data, and then it takes care that condition monitoring and structural health monitoring. That means actually that machine life, that sometimes it gets worn out, and after some working hours it may not it may get faulty. That and that will take care. That's a structural health monitoring. And remote diagnosis, that means watching how the machine is working, all those things, and remote control, and it is able to operate that particular machine also. That is this system is called actually cyber physical systems, enable communication, monitoring and control. Now this will take care the industry equipments, different industries, that is a smart factory, smart city, and smart grid, smart logistics and smart products, like that. So this is individual thing. Smart factory means this can be controlled by means of this CPPS communication monitoring control devices. Okay, and here I would like to know the Internet of Things. Now only I am talking about this one. It's a system of interrelated computing devices, mechanical and digital machines, objects, animals, or people, it's a human, that are provided with unique identifiers and the ability to transfer data over network without requiring human to human or human to computer interactions. It is communicating objects based on internet technologies. Okay, so normally this every IoT component, it is having some sensor linked product, and it has some separate IP numbers for this. Okay, that is the important thing. Here you see there are RFID, and then this the scanner. Okay, and Bluetooth and Wi-Fi. These are all coming under the IoT elements only. Okay. Then that iOS, it is Internet of Service, is a commercial transaction where one party grants temporary access to the resources of another party in order to perform a prescribed function and a related benefit. Resources may be human workforce and skills, technical systems, information, consumables, land, and others. Okay, so that means once the product is sold out, that product informations can be monitored continuously, and the service provider he can take care the issues. That is the thing. It is it is a product based service on demand, knowledge provision, and services for controlling the behavior of the product. It is an interaction between people, machines, and systems to improve added value. Okay, so the Internet of Services may be in the form of smart logistics or smart production processes and smart engineering. Any form it may be available in real time implementation. Some example here: the Rolls Royce does not sell engines to airlines these days. So instead of selling that engines, what they do, instead of it sells airlines in hour flown. That means how many hours it is working, like that only. There's some contract like that it will give. Okay, hours flown, selling the hours flown only, and a service contract to maintain the leased engines. That is, the airlines get a free engine when they sign up. That's all. Okay, that means they will get the free engine, and they monitor that manufacturers. They monitor Rolls Royce. They monitor how many hours it works. They know after some hours this attentions need to be given to that engine, so that they will take care of all those things. That's all. Okay, so the hours flown only is important for the sales items in that case. So that's why it is called service. And there could be a company which does not sell the smoke alarms directly. Smoke alarms they will not deal directly, but instead it installs the smoke alarms in your home. The alarms would report their status back to your insurance company. That's all. Or the boilers which report a fault and book in a service while you sleep. That's what. So this is the service is unknowingly it will happen to the human knowledge. And next thing is Internet of Data. That's the data is the major role in technologies, the present technologies. So the Internet of Data is managed through Internet technologies. Cyber-physical systems are producing big data, and the challenge is development of holistic security and safety culture. You can see here this picture. You can see that the Internet of Ideas, the Internet of Data, and Internet of Things, and Internet of People are there. So this is for simple understanding. The figure is given here. And another thing, Internet of Data can share its values along with the Internet of Things, and it also can share Internet of Services. Okay, so this all put together, we can see that embedded things of Internet of Artificial Intelligence is working out in this point. Okay, in abstract of this cyber security system, cyber physical systems. The cyber physical systems monitor physical processes, create a virtual copy of the physical world, and make decentralized decisions. Cyber physical systems communicate and cooperate with each other and humans in real time over the Internet of Things. Both internal and cross organization services are offered and utilized by participants of the value chain via the Internet of Services. Now, this is one more explanation I want to give you. This is a contributing digital technologies in an industry. Here, I said industry 4.0. Okay, here this can be decentralized into digitization into three space actually. First one is digitization and integration of vertical and horizontal value chains, and this one is digitization of product and service offerings, and this one is digital business models and customer access. Though these three informations will operate the industry 4.0, and these three informations is data and analytics or core capability in this case, and this all will get the information through these elements. That is what. Okay, and here some computer softwares which is supporting this Internet of Things and manufacturing activities. Here you see the modeling and enterprise management software in use. It is SolidWorks, it is CAD. CAD can be developed by Dassault Systems, and Windchill, it is a product lifecycle management software by PTC. Product Center, it is also supporting PLM, which is developed by Softtech, and Top Solid, it is also useful for CAD/CAM development by Missler Software, And PDExpert, it's a PLM by active sensing. Team Center, that is also for PLM only. And Autodesk Inventor, Autodesk Fusion, CAD CAM CAE supporting cloud actually. And SAP PLM, it is ERP by SAP. So these are all the softwares which is interconnected with this Internet of Things and artificial intelligence industry 4.0. Okay, and this all do this jobs actually, virtualization, VRML and AutoML, Python, classification algorithm and regression algorithms can be done by using this all packages. And the example, the Siemens, they used this industry 4.0 effectively for their product. Actually, the German manufacturing guy Siemens, an industrial user, is implementing an industry 4.0 solution in medical engineering. And for years, artificial knee and hip joints were standardized products, with engineers needing several days to customize them for patients. Now, new software and steering solutions enable Siemens to produce an implant within 3 to 4 hours. Like some softwares are there actually. I'm not getting exactly. Let me check. Another thing is the company, it's Trumpf. Actually, German tool maker Trumpf, an industry 4.0 supplier and worldwide market leader of laser systems, has put the first social machines to work. Each component is smart and knows what work has already been carried out on it. Because the production facility already knows its capacity utilization and communicates with other facilities, production options are automatically optimized. So this the whole machine itself, industry 4.0 is implemented. And another video which is utilized in that automotive industry, okay, that I can show you now. Actually, it gives more clarity how the Internet of Things, which is working in any manufacturing industries. In fact, it is in automotive industry is shown in for the presentation. So we can understand very clearly how the things are verified and how the quality control is takes place. Everything is witnessed here. And another thing, yeah, some examples of product evolution is connected and smart products. You see that Philips lighting. Okay, the users can control Philips lighting, hue light bulbs via smartphone, turning them on and off, programming them to blink if they detect an intruder, or dimming them slowly at night. Okay, so this is some facilities here. It is represented the same way. Medtronic, actually, it's a implanted digital blood glucose meter, connects wirelessly to a monitoring and a display device, and can alert patients to trends in glucose levels requiring attention. Okay, this is another thing. The cert, Polo Tech cert. Okay, it monitors the calories burned and movement intensity and heart rate and other data of wearers mobile device, etc. And this is the tennis player. He can read the ball speed and spin and impact location, and how to improve the game, all those things. These are the some facilities which is available in the market. Okay. So now the question is whether it is a virtual reality or augmented reality. That is a question. So it is automatically virtual. There is no point of virtual aspect in this point, only that improving the facility of any available products. Okay, so it is all coming under that augmented reality aspect only. Okay. And another thing, it is the example, the BASF North America company, with deployment of connected systems and advanced analytics models for predictive asset management and process management and control and virtual plan commissioning. So the company completely automated the production of liquid soaps at its smart pilot plant in Kaiserslautern. Once a user places an order for a customized soap, the radio frequency identification tags attached to the soap containers inform the equipment on the production line via wireless network connections about the desired composition of the soap and packaging, thus enabling mass customization without human involvement. So these are all one more company which they effectively implementing that Industry 4.0 in their liquid soap manufacturing company. So here, any industries, it has some ultimate aim to bring their advanced technologies in their companies. So here some points: the predictive asset management, prediction of breakdown for them, they are mostly required, and process management and control, and energy management aspect, and safety management aspect, and production simulation aspect, supply chain management aspect, and demand forecasting, and additive manufacturing for the testing, advanced analytics and selecting materials, and smart products and services through IoT, that is smart sensor. So these are all the scopes or adding up any industries to make into the level of Industry 4.0. And some countries involved in Industry 4.0, it is actually the smart manufacturing. It is named in US, and made in China 2025, it is in China, that is equivalent to the Industry 4.0. And in South Korea, it is termed as manufacturing innovation. And in Japan, it is termed as industrial value chain initiatives. And in Singapore, it is termed as smart nation program. So these are the different countries with the different names. They are implementing the Industry 4.0 for their countries. And here I would like to discuss in detailed way whether the font which is eligible to the audience or not, I don't know exactly. Anyhow, if you like, I can share the presentations PPT also. Let them see, and you see that here the factory of the future, how it looks. What are the things they're expecting for the future factories? Here you see the first point. Machines self-optimize their parameters on the basis of material input and process parameters. Okay, so if they find any weakness on themselves, they can develop that, they can remove their weakness, and they can fulfill the full-fledged equipment. That's that is artificial intelligence, and what is called that neural network. By using that, all we can develop in this way. And artificial intelligence systems dynamically optimize warehouse utilization, taking into account material overflows, inflows, inventory levels, and turn rates. Everything artificial intelligence systems will take care. And artificial intelligence systems predict maintenance needs by identifying failure patterns. So by seeing the previous history, it is able to find out when possible failures, and from the machine worn out points, from the cloud data, and the sensors which sends the data to the cloud, and from there it can take the data and analyze and find out when the possible time of failures. That maintenance aspect will taken care by artificial intelligence. And virtual agents verbally provide operators with the inform from IT systems upon request. And artificial intelligence systems predict quality issues by analyzing and learning from quality and process data. So not only from the quality department, from the user end also, they can find out the quality issues, and it can be rectified in the real-time production area. And assistant system suggests solutions to incidents based on earlier failure reports. And automated guided vehicles carry parts, detect obstacles, and adjust their routes. This is AGV things already we are come across in the flexible manufacturing systems studies. And artificial intelligence systems develop new products based on generative design principles. And now here the robots use image recognition to automatically adapt to the changing locations of parts. It can store the images, and by compare that image with that real-time production, and according to that image, it can adjust itself and do the process. And artificial intelligence systems detect quality defects through image recognition. This is also more useful in the day-to-day production area. And artificial intelligence systems accurately predict future demand for products by learning from the patterns in the demand and environmental data. So especially from the service, internet of services, this can be observed. Okay. And this is artificial intelligence in defining manufacturing. So the predictive maintenance and demand forecasting and inventory optimization, whatever the points we discussed in the previous slide, here in other form it is given here. Okay, intelligent data security solutions, human robotics collaborative ecosystems, intelligent factory operations, and the application of digital twins, all those things, it is interconnected with that artificial intelligence in manufacturing. Now this is the topic, the being a mechanical engineering people changing their interest into internet of things and artificial intelligence entities. It is a really little tough only, but the things are required for future. That is important thing. So I can suggest the people, they are with a master's degree and they are planning to do their PhD in future things. Better you can prefer some internet of things and artificial intelligence area, and do some industry 4.0 side research works. That will be more useful for your updating your knowledge, as well as that demand in future requirements also. Here the real-time control and monitoring, there are some scopes, cyber physical machine tools you can do, and real-time control machine mechanisms you can take up and do your work. And cyber physical 3D printing also, there are additive manufacturing, there are a lot of scopes are there. And internet of things, you can find out the present automation industries. Then what are the data which is available, the data can be transferred to the internet of things, and how it can be analyzed, and things can be studied. And wireless communications and manufacturing automation, additive manufacturing, manufacturing robots, and logistic automation, that especially that supply chain management, and human machine interaction, and automatic guided vehicle. etc. There are these are the scopes for the research in future. So with this, I can wind up the session, and thanks for listening my session. Now the time is 11:45 exactly. I took 1 hour. Thanks for providing me this chance. Thank you. Any questions or any interactions, you can come.
Thank you, sir. Thank you so much. Thank you so much for sharing your deep knowledge, sir. Sir, I have collected some questions for you.
Yeah.
Sir, can mechanical students study artificial intelligence and how it will be useful?
Yeah, actually, mechanical students, it is recommended to study artificial intelligence, and especially this is useful to analyze the data, especially the data analysis. It is very important thing. So now that neural network, that machine learning, and natural language algorithms development, these all have a lot of openings in that mechanical students also. So only thing they supposed to have some patience to learn the terminology. The terminology is really they may not adapt with this. Okay, especially the faculties, they supposed to have some inclination towards this technology. That is an important thing. So I am suggesting students can learn, and it is important.
Sir, one more, sir. Where is augmented reality being used the most?
Yeah,
Sir?
actually, yeah. So actually, that wherever that improvements is possible, and that realization of the product which is in the function, there you can enhance the applications, and you see exactly, if I want to say, augmented reality. That the presentation itself, I have sent that 4 examples, no, that we can say.
Okay, sir. Okay, thank you, sir. Thank you for sharing your knowledge. I now call upon Mr. Bhuneshwaran, Assistant Professor, Department of Mechanical Engineering, Sri Balaji Chokalingam Engineering College, to deliver the vote of thanks.
Good morning to all. I deem it is my great honor and privilege to propose the vote of thanks on this memorable occasion. First and foremost, I thank our Honorable Founder Chairman, Dr. A.C. Shanmugam Sir, Sri Balaji Chokalingam Engineering College, Arni. I also express my heartfelt thanks to our beloved President, Engineer A.C.S. Arun Kumar Sir, Sri Balaji Chokalingam Engineering College. My heart goes out to thank our respected Secretary, Mr. A.C. Ravi Sir. Next, my sincere thanks to our principal, Dr. V. Thirunakarsu sir, for his unstinted support for this webinar. Also, I thank our vice principal also. I express my deep gratitude to our chief guest, Dr. S. Ramesh sir, Professor Mechanical Engineering, Presidency University, Bangalore, for this valuable and elegant webinar presentation. Specifically, I am highly indebted thanks to Dr. Manivannan sir, Dean, Phase 2 campus, MGR University, Chennai, for inspiring us and supporting us. My grateful thanks to various department HODs, teaching and non-teaching faculties for this valuable contribution in all our efforts. I must mention our deep sense of thanks to Dr. Ismail sir, Vijayalakshmi madam, and I extend my thanks to Radha madam for the wonderful time management. Finally, I convey my hearty thanks to the participants for active participation in this event. Thank you once again all.
Thank you, sir. The feedback cum assessment form is available in the YouTube description box. Participant can request it to complete and submit their form before today 10 p.m. After that, the form will be deactivated. The e-certificate for the participation will be sent to your registered email in 2 working days. I repeat, the feedback cum assessment form is available in the YouTube description box. You are requested to complete and submit the form before 10 p.m. Later, the form will be deactivated. The e-certificate for participation will be sent to your registered mail in 2 days. On behalf of our organizing committee, I would like to I request Mr. Ismail Khalilullah to post appreciation certificate. On behalf of organizing committee, I would like to thank our speaker of the day, Mr. Ramesh Sengottuvelu, for his wonderful presentation. Thank you, sir. The feedback cum assessment form will be in the description box. You are requested to complete and submit your form before 10 p.m. today. Later, the form will be deactivated. The e-certificate for participation will be sent to your registered mail. As per our policy, we normally won't request the speaker to share their PPT, but at the same time, our video is ever available in the YouTube channel. Participant can view at any time. We have come to end of the program. Hope everyone had gained knowledge. With this satisfaction of presenting a good webinar, we wish to sign off and meet you in the next program. Don't forget to submit your feedback and subscribe our YouTube channel, Dr. MJ University, Phase 2 Digital Learning. Thank you. Stay home, stay safe.